Okay, let's look at this is example 4.8 in the book. This is a good example of you have a sign of uniform density that weighs 270 pounds and it's supported by a ball and socket joint at A by two cables. So we're supposed to determine the tension in each cable and the reaction at A. Okay, so let's draw a free body diagram of this thing if I can. See if I can not make any mistakes here. Okay, so I'm going to redraw it. They always did this at an angle. I'm going to try to draw it like this. So you have this sign like this, right? So here in the middle is where you have 270 pounds coming down. Here at E, you have a force going off in that direction somewhere. I'm going to call this CE, right? And here at B, you have a force going off in a different direction. I'm going to call this BD. Okay, here's your X, Y, your X, Y, and Z. And the other thing that we're missing is here we have the reaction at A. So we have I'm just going to draw it in the direction of the positive axis just because I have absolutely no idea where it's going to go. And so it just makes the math a little bit easier. It's not like it matters. So this is AX, AY, AZ. Again, if I knew where it was going, I might be inclined to draw it in that direction. And then if you get a negative number, it means it's in the opposite direction. With 3D problems, I will tend to just draw them in the coordinate axes directions. So what are we going to do? Well, basically it comes down to this. Sum of the forces is equal to 0, and sum of the moments equal to 0, right? So we're going to sum up all the forces in x, y, z, set them to 0. Sum up all the moments in x, y, z, set them to 0. So in general, I find that it's almost always easier to do the moments first because when you're doing the moments, you can actually you can selectively pick points to get rid of unknowns, and so you don't have to solve 5 equations, 6 equations simultaneously. You can get rid of it and just have to solve 1 or 2 equations simultaneously. It's just easier. It's not right or wrong. It's just easier. So how are we going to do that? Well, where should we take the moment? If we take the moment about this point right here, okay, will that work? Yes. Yes, it will. It'll work fine, but it'll just be hard. There's no reason to do it. When you're taking the moments, you want to pick somewhere that helps you out. That's, again, the whole purpose of taking the moments is some of the moments anywhere on or around or anything to do with this object. Yeah, I could take the sum of the moments up here, some random space, and the sum of the moments is still going to be 0. But I'm going to choose to take the sum of the moments here because then all the A things go away. So I want to take the sum of the moments at A. So sum of the moments at A is equal to 0. Now, moment in general, right, is R cross F. So I need to define my R's and F's, and this is what I would like you guys to do when you're working on your homework. I want to be really clear on defining it. I'm going to define my CE. What is CE? Well, it's the magnitude of CE times lambda of CE, right? This is CE. So it's CE times the unit vector in the direction from C to E. So from E to C, right? Because we're at E. So from here to wherever it is that is, to point C, it's going to go minus 6 in the I direction. It's going to go plus 3 in the J direction, 3, and it's going to go plus 2 in the K direction. But that's not a unit vector, right? That's just a vector, so we need to divide by the sum. It's square root of 6 squared plus 3 squared plus 2 squared. So this works out to be, so CE is equal to the magnitude CE times, and it's minus 6/7 I plus 3/7 J plus 2/7 K. We're going to do the same thing for BD. BD is equal to BD times from point B to point D, right? We have minus 8 in the I direction. We have plus 4 in the J direction, and we have minus 8 in the K direction. So all that divided by 8 squared plus 4 squared plus 8 squared, which works out to be 12. So this is BD is equal to BD times, so 8/12, so it's minus 2/3 I plus 1/3 j minus 2/3 k. Now both of these, you should be able to take this and do the sum of the squares of 2/3 squared plus 1/3 squared and 2/3 squared and get 1, which you do, and same with up here with the CE. Now, just for, because I know I'm going to need it, let's also put this, let's say the weight is minus 270 in the j direction, right? And now let's define our r's nice and clearly, because we're going to do a bunch of r cross f's, right? So from our r from A to point E is simply 6i, right? And our r from A to B is 8i. And our r from A to the CG, right, from A to the C, where the weight is applied, is going to be 4i, is because the weight is going to be applied right here in the middle, right, so as we showed here. So it's going to be 4 over and 2.5 down. So 4i minus 2.5j. Okay. So now let's go to our sum of the moments equation. So I'm gonna have to scroll up. We're gonna be scrolling back and forth a little bit here, but we're gonna say sum of the moments at A is equal to 0. So what do you have? You have all your forces. So you have your weight. So it's, sorry, let's fix that real quick. It's R cross F, right? So you have your R from A to CG cross the weight, right? Plus R from A to E cross the force at E, and the force at E is the CE vector, right? So cross, I'm just going to write CE like this, we'll fill in the rest, plus R from A to B cross BD. Okay, so now as you set up that equation, then it's really a series of equations. Let's actually work it out. So R from A, so let's do this, right? So you have I, J, and K. R from A to CG is 4, 2.5, and 0. And the weight is 0 minus 270 and 0, right? Plus I, J, K, and R from A to E is 600, and CE is, you gotta scroll back up here again. I'm gonna pull the CE out here. It's multiplied by everything, right? And it's gonna be minus 6/7, 3/7, and 2/7, plus another determinant, I, J, K. R from A to B is going to be 800, and the other one's pull the BD out here, minus 2/3, 1/3 minus 2/3. Boom. That's BD. Okay, and so then this gives us a bunch of equations. Let's actually work out what this is. I'm gonna do this, excuse me, in a little bit of a, I'm gonna look at the I terms, right? So for I term from here is gonna be this times this, and this times this, so it's gonna be 0. The I from this term is gonna be plus CE, and it's gonna be 0 again. So this is 0, sorry, 0 plus, and then the I from this one over here is gonna be the same deal. This times this minus this times this, so that is 0. So there's no I terms. Then I'm going to do minus j. This is how I do determinants. I do I minus j plus k just so I can stay in the same order. So if you look at the j term, it's going to be 4 times 0, 0 times 0. That's still a 0 from there. Now let's look at this one. If we look at the j term, it's going to be 6. It's going to be c plus ce times 6 times 2/7 minus 0. So that's going to be that. And then look at the last one. Look at this j term over here. And we have plus BD. And then here you have the 8 times, so minus, and so it's 8 times minus 2/3. And then plus 0. And then lastly, plus the k terms. Here the k term is definitely 4 times 4 times minus 270 from the weight. The next one, the k term is going to be plus CE times 6 times 2/7. 3/7, because we're looking at the k term. 3/7, right, plus 0, or minus 0, sorry, plus BD times 8 times 1/3. Okay, so that is the equation, right? It's I minus j plus k, all this is equal to 0. So then what do we do with it? Well, from there, we just set each term equal to 0. We take the I terms, and we set the sum of the forces in the I direction equals 0, which this tells us nothing, right? So there's no information in this equation, so that's fair enough. And then we take the j terms, right? So let's look at the j terms. We have CE times 12/7 is, sorry about that, is equal to, or minus BD times HL, so I can put that on the other side. No, I'm sorry, let's just stick with, so let's say that's minus BD times 8 times minus 2/3 equals 0. So therefore, that can tell us that CE, excuse me, CE is 3.11 times BD. This is just a minus there. So that's, again, that gives us a relation with each other. Still not an answer. So let's look at K terms. Here we look at 4 times 270, so minus 1080, plus CE times 18/7, plus BD times 8/3, right, is equal to 0. So put the 1080 on the other side. I'm going to use this equation right here, replace CE for that, and you end up getting that BD is equal to 101.25, and therefore CE is equal to 315. Okay, so now we found our two tensions, 101.25 pounds and 315 pounds. So that is the tension in this cable right here and the tension in this cable right here. So then the last thing it asks for us is the reaction at A. So you remember when we did the sum of the moments, we're looking here at this free body diagram. When we did the sum of the moments, we pictured about A so we can get rid of AX, AY, AZ. Well, now we need to figure out what AX, AY, and AZ are. Well, this part's actually the relatively simple part, is you just do sum of the forces in X equals sum of the forces in Y equals sum of the forces in Z, which is a big fat 0, okay? So in the X direction, we have AX, and notice I drew it in the positive direction, so AX plus, and then here's where let's come and I'm going to look at this right here. Our CE in the X direction is CE times minus 6/7, right? So I'm just going to put minus 6/7 CE, and then in the BD it's minus 2/3 BD. Minus 2/3 BD is equal to 0, and since we know BD and CE, this gives us that AX is equal to 337.5. 337.5. Sum of the forces in Y equals 0. That gives us that AY plus, now we're going to look at the Y terms. The CE is going to be plus 3/7 CE. So plus 3/7 CE. And then the other one is going to be plus 1/3 BD plus 1/3 BD equals 0. again, that tells us that AY is equal to 101.25. So here's AX, here's AY. And then lastly, we take the sum of the forces in Z equals 0. So, oh, I lied on that one. That was my fault. I'm going to see if I can erase this somehow. How did I lie? Well, this is, although this is all true, get rid of this, boom. We forgot a term. And what was that term that we forgot? We forgot minus 270 equals 0. So you have to account for the weight. That's because our weight is in the j direction, right? And so that tells us that, scratch this, not yet. AY, the number I put was right. It's 101.25. But you have to account for that weight. That's how you're going to get that. And lastly, sum of the forces in Z equals 0. So AZ, and then come up here, it's going to be plus 2/7 CE and minus 2/3 BD. So plus 2/7 times CE minus 2/3 times BD equals 0. And that tells you that AZ is equal to, in this case, it's a minus 222.5. So you could write the A is equal to 337.5 in the I direction, plus 101.25 in the J direction, minus 22.5 in the K direction. So that would be a nice way to express the final answer there. And that's that. I say that's that. I realize it took a while to do this, but it's simply a matter of going through. So a quick review. You go through and you pick somewhere to take the moments. You can pick anywhere you want to take the moments. You're going to get the same answer no matter what, but there's just places that make your life easier. And so picking them here at A, it just makes your life easier because you get rid of 3 unknowns. So all you have left are 2 unknowns. You go through and you do your sum of your moments equations, and you can solve for those unknowns. Now, I would advocate strongly and suggest for the tests and for this class and for when you're doing homework, do this stuff. Go through and really clearly define all the vectors. Don't be trying to do it on the fly, because then when you say, hey, it's this R from here to there cross this F in that direction, well, then what is that R? From the A to E, it's boom right here, and I can just look it up. This one's really simple because it's just in one axis, but once you start having things off in different axes, it makes it a lot easier to be really explicit like that. And that's that. That's your answer.